Okay, this is the homework answers for chapter 13, which is the gas laws and heat of expansion. Well, primarily the gas laws. And the first problem we want to look at is just a simple conversion. It's number 4 in the book. And it states that a tungsten light bulb element operates at 2900 degrees K. What is this in Fahrenheit temperature and what is this in Celsius? And I read both of them together because you really have to do the Celsius first to make this simple. So you have 2900 K, and we know that K is equal to Celsius plus 273. So that means that Celsius is going to be K minus 273. So in this case, it's going to be 2900 minus 273, which is going to equal 2627. And if we round that to two significant figures, we get 2600 degrees centigrade. Now we take that to get the Fahrenheit. We know that Fahrenheit is equal to 9/5 centigrade plus 32. So we're going to be 9/5 times 2600 plus 32, and that will equal 4760, which is 4800 to two significant figures. So that's problem number 4. Now with problem number 10, we're looking at thermal expansion of solids and liquids. And the fundamental, before we do problem 10, the fundamental problem, or the fundamental equations, is that the change in length is equal to the original length times alpha, which is the coefficient of linear expansion, times the change in temperature. And that change in temperature for most of the tables that you'll see is in centigrade. Now the change in volume is going to equal the original volume times something called beta, which is the coefficient of volumetric expansion, times the change in temperature. So it's essentially they're very similar. So for this first problem, we have how much taller does the Eiffel Tower become at the end of a day when the temperature has increased by 15 degrees if its original height is 321 meters, and you can assume that it's made of steel. Okay, so how much taller? Delta L is how much taller is equal to 321, which is the original height, 321 meters, and the change in temperature, well, let's put the coefficient of linear expansion for steel, which is 12 times 10 to the minus 6. And then the change in temperature is 15 degrees centigrade. And if you do the math here, you get 0.058 meters, or 5.8 centimeters. So the change in height for the Eiffel Tower at the middle of the day when it's hot is 5.8 centimeters taller than at a time when it's cooler. Problem number 12 is very similar. Problem number 12 states how large an expansive gap should be left between a steel railroad rails if they reach a maximum temperature of 35 degrees greater than when they are laid. Their original length is 10 meters. So they have to leave a gap, and this is what causes sidewalks to buckle, and why they put linear cracks in sidewalks is to give them a place to expand. So the change in the length of the rail, they have to put a little gap in there, is equal to the original length, which in this case is 10 meters. And again, we're talking about steel, so that's 12 times 10 to the minus 6. And now the predicted maximum change in temperature is about 35 degrees centigrade, which is actually quite a broad gap in temperature. And if you do this calculation, you get 0.0042 meters or 0.42 centimeters. So about a half a centimeter. To be safe, they might put 0.6 or 0.75 just to be safe. 0.5 would be cutting it pretty close as far as a distance. 5 millimeter gap between rails would be pretty close. Now number 19 is the next problem, and number 19 is a volume expansion problem. So we have to look at this equation as opposed to the previous. And what it says is that a physicist makes a cup of instant coffee and notices that as the coffee cools, the level drops 3 millimeters in a glass cup. Show that this decrease cannot be due to the thermal contraction by calculating the decrease in the level if 350 cubic centimeters of coffee is in a 3 centimeter diameter cup and the decrease in temperature is 50 degrees. And then it tells you that most of the drop in level is because of loss of gas inside the cup or inside the coffee. Now, so we have a 3 millimeter drop. Now, just to put this all in the same units, that's equal to 0.3 centimeters. And the volume, the original volume of liquid is 350 cubic centimeters. You're going to need that right there. And the other thing you need to know is what the cross-sectional area of the cup is. The cross-sectional area of the cup is going to be equal to pi times its radius squared. Its diameter is 7, so the radius is 3.5. So that's going to equal pi times 3.5 squared. And that's going to be, so the cross-sectional area of this cup is 38.5 centimeters squared. So, in order to calculate this, you have to realize that both the cup and the fluid are contracting. And so you need the volumetric expansion for the fluid, which is essentially water. Coffee is 99.5% water. And if you look up water, you get 210 times 10 to the minus 6. And that's water. And then the glass cup is equal to 27 times 10 to the minus 6. So this tells you that the water contracts more than the cup does as the temperature falls. And so the change in volume inside the cup is going to be equal to the original volume, which we have up here, times the difference between the two coefficients of contraction, and then we'll multiply that by 10 to the minus 6 times the change in temperature, which is 50 degrees. And so the original volume here was 350. We put that in, and the change in volume is 3.20 cubic centimeters. Now, how far would it drop if the change in volume was the only thing that was making it drop? How far would it drop? Well, if you take this change in volume and you divide that by the cross-sectional area, which you calculated up here, then what's left is the height that it drops. And in this case, that height is 0.0831 centimeters, or 0.831 millimeters. And what you can see is this 3 millimeters is quite a bit more than this 0.381. And so what that shows is that most of the drop in level is not due to the difference in coefficient expansion. It's due to the loss of something else in the fluid. And as it turns out, it's the loss of gas within the fluid. The next problem is problem number 25. And with problem number 25, we're moving into a new area, the area being the ideal gas law. And the ideal gas law is PV is equal to nRT. P is pressure, V is volume, N is a number of moles, R is the gas constant, and T is temperature. Now, what R is, the value for R is controlled by the units that you select for your pressure, volume, pressure and volume essentially. You're always going to use Kelvin for temperature, and you're always going to use moles for moles. And so the value of R is going to be driven by what you select for P and V in terms of units. So for example, if you express P in atmospheres, whereas 1 atmosphere is equal to 1.01 times 10 to the 5th pascals, and it's also equal to 760 millimeters of mercury. If you use atmospheres, and V, if you use liters, then R is equal to 0.0821. And as you can tell, I use this a lot, and that's why I know this. Now, if you want to use a different R, then what you do is you put in, for example, you'll put 1.01 times 10 to the 5th, and that's the normal pressure at standard temperature and pressure. For volume, you'll assume 1 mole, and molar volume is 22.4, and then that's 1 mole of gas. R is what you want to know, and then T is 273, or 0 degrees centigrade. And if you solve this equation for R, it will tell you what R is when you express liters and pascals instead of liters and atmospheres. And I actually don't know what the answer to that is. You can do that if you like. You can see that this is going to be like 2 times 10 to the 6th, 1 times 10 to the 4, something like 1 something times 10 to the 4 for that. If you put 760 in here and put everything else the same, then you can find R when pressure is expressed in terms of millimeters of mercury. Well, I've always remembered this number, and so I change whatever pressure they give me into atmospheres by dividing by this number or by this number, depending on what they give me. And then make sure that my volume's in liters. So let's take a look at the first problem, problem number 25. Problem number 25 states, a large helium-filled balloon is used to lift scientific equipment to high altitudes. What is the pressure inside such a balloon if it starts out at sea level, assuming that pressure at sea level is 1 atmosphere, with a temperature of 10 degrees and rises to an altitude where the volume is 20 times its original volume and the temperature is minus 50. So P1 is equal to 1 atmosphere. They tell you sea level, that's your assumption. T1 is equal to 283, which is 10 degrees centigrade expressed as Kelvin. And V1 is equal to V1. P2 is what you want to know. It's what you don't know. T2 is minus 50 degrees centigrade, which is 223 degrees Kelvin, and V2 is equal to 20 V1. And we know that P1 V1 over T1 is equal to P2 V2 over T2. So that 1 times V1 over 283 is equal to P2, which is what we don't know, 20 V1, that's what V2 is, divided by 223. Now the V's here cancel out, so because they're on both sides of the equation. So if we cross multiply here, we have 223, which is 1 times 223, is equal to 20 times 283 times P2. And P2, if you do the math here, ends up being 0.039 atmospheres. Now, if you wanted to convert that, you could multiply that number times this if you want to convert it to pascals, or you can multiply by this if you want to convert it to millimeters of mercury. Now, the second part of this question is, what is the gauge pressure? Well, a gauge subtracts the surrounding atmosphere. So it tells you whatever the pressure is over or under 1 atmosphere. In this case, the pressure is 0.039 atmospheres, and you would subtract 1 atmosphere because that's what the way the gauges are set up. So you would end up with a minus 0.961 atmospheres would be the gauge pressure. Number 28 is very straightforward. Number 28 states, it asks you to calculate the number of moles of a 2-liter volume of air in the lungs of an average person, knowing that the temperature is body temperature of 37 degrees. Now, because they don't tell you, the assumption here is that you're dealing with a pressure of 1 atmosphere, or sea level pressure. So PV is equal to nRT. So N is going to equal PV over RT, which is 1 atmosphere times 2 liters. They gave you that, divided by 0.0821 is the value for R when you're using atmospheres as your pressure and liters as your volume. And then body temperature is 310 degrees Kelvin, expressed in Kelvin. If you do the math here, you get 0.0786 moles of gas. 0.0836 moles of gas.